One of the things that is nice about the new content is that all these conversions and calculations are gone. Okay? So we don't have to do any more kind of conversions or calculations, but what we do have to do is understand some basics of what defines a molecule and how do we apply those basics to larger interactions. Okay? So where this is really coming in is with our forces. Okay? Ultimately, the forces, as a big concept, are what represent virtually everything we see in the world. Okay? We are aware of other forces that actually aren't on this list, because ultimately this list is just looking at intermolecular. What does intermolecular mean? Between different molecules. We also have a force that represents the attraction within a molecule, known as intra. Oh my gosh, maybe I need a pen. Oof, that looks even worse on the screen. We also have intramolecular, meaning within the molecule. What are the forces within a molecule? Wait, there's a force within a molecule? Right. Ultimately, chemistry, beginning to end, regardless of the division, where you're located in, be it physical chemistry, general chemistry, organic, biochem, any of that is really only looking at one thing. It is the type of force. It is the force, the attraction between any two particles, period. Okay. That is all we do. The calculations that you're running are all dependent on that force. Okay. It's just a question of the levels of quantification that we find within that attraction. Okay. So if I take a look at any two things, well, and what are my things if I'm looking at all of matter? I can get two answers out of that. Atoms, okay, the largest of our things. Okay. We could go even smaller than atoms. We can look at the attractive force between electrons and protons. Okay. If we look at the attractive force between those two objects, what we're now moving into is quantum physics. Okay? Or depending on where it's taught, because physicists talk about it and claim that as their own, so they call it quantum physics. And then chemists do the same thing. They claim the exact same content, but they now call it quantum chemistry. Okay? So we could go through and look at that. You don't want to. You just want to deal with the simplest aspect of that. The electron is attracted to the proton. The proton is detracted? Not attracted? Unattracted? Repelled, there's the word, from other protons. Electrons are repelled from other electrons. So we get the opposite charges attract. Right? Like charges repel. That allows us to come up with the basis for atomic structure. Once we have an atom, we can then compare how that atom, now a larger unit, interacts with another unit, being another atom. Depending on that level of attraction, we can define that as either an intramolecular attraction or an intermolecular. Intramolecular meaning those two are so strongly attracted to each other that they don't move away from each other very much. Okay? Kind of like a married couple. Most, well, ideal married couples. Okay? Ideal married couples don't move. Well, my wife is not standing next to me. That's kind of what I'm referencing there. If we look at the emotional connection in couples, okay, couples have a stronger emotional connection than single people with each other. Okay, so we can use relationships to help us kind of establish those connections. Okay, if they have a stronger connection, we now don't call them single people. We would call them couples. If they have an even stronger attraction, what would we call them? Married couples. Okay? So just within relationships, we have the exact same fundamentals that are happening in chemistry. Okay? How are those things attracting to each other? and they attract to each other in different amounts. If they attract to each other really, really strongly, we might call them married. If they're only partially attracted to each other, we might call them couples. If they're less strongly attracted to each other, they're just testing it out, they might be.
It's complicated.
Fair enough. It's complicated, okay? Or dating. Okay? If there's zero attraction whatsoever,
The friend zone.
that's a nice way to add levels into this, we could end up with the friend zone. Okay? The only reason you're in a friend zone is your own fault. It has nothing to do with the other people, by the way, just for the record.
I don't know. I'm a 10 out of 10, so.
That could be the problem.
I'm just too attractive for other people.
That's exactly what I was saying.
I know, it's tough. They're intimidating.
Okay? Just like me, we're intimidating.
Yeah.
Okay? So molecules are doing the same thing, or atoms are doing the same thing. If that atomic attraction is super, super strong and they're now married, okay, or they're couples, okay, I'll refer to that as a bond. Well, what kind of bonds are there? Okay, we could run with James Bond. What would be an insanely strong bond? Couple or a married couple that's been together for 80 years. Wow. Is that possible? That is possible, right? Okay. Like just life expectancies and all those. Yeah, if both people lived to be 100 and they got married, yeah, that's possible. Okay, 80 years. Okay, that is an insanely strong attraction between those two people. Okay, what would their attraction be to the rest of single people? Probably bleh. Why? Because they spent 80 years with each other, they're attracted to each other and each other only, they don't care about anybody else. We get an insanely strong attraction between those two people. Okay, we move to bonds now. I get an insanely strong attraction between those two people. They're now equally sharing their entire lives, and they have zero interaction with the rest of the world. We can call that a nonpolar covalent bond. Okay. Equal sharing of electrons. Notice in that 80-year-old, or 80 married, whatever, long marriage, we said they had zero attraction with the outside world. Why would they have zero attraction? They're only attracted to each other. Okay? So they have zero attraction outside of their bonding situation. What is outside a bond? Forces are intramolecular attractions. So a nonpolar covalent bond is such a strong attraction that it has virtually zero need to interact with the outside world. That gets known as our London dispersion forces, or our van der Waals forces, or our induced dipole forces. Okay? I think that one personally is dumb. Okay? It's just easy to stick with this. Okay? For this class, we almost always refer to it as LDF, ultimately because, well, not necessarily your fault. I'm lazy, and I don't want to write it all out. So I refer to it as LDF for London dispersion force. Okay? What happens if instead of being that been married for 80 years, they've been married for, where's that threshold? Anybody know where that threshold is? Where you, they used to call it the 7-year itch. Anybody heard of that? Some people have. Allegedly, there's an amount of time that you've been married, and at that time, that's when the most marriages fall apart. Because you realize, holy crap, I have to spend the rest of my life with this person. Okay. And it's not 7 years, but it used to get called the 7-year itch, or 7 years. I think it's shrunk significantly, but also so has the... It's 3 years? Holy crap. Wow. Okay, so at that 3-year mark, they aren't super attracted to each other. They're still married, okay? So they're still sharing, but they're like, I don't really know. Maybe, maybe not. 70 more years with you?
You say it like that? Man, I gotta go.
So they may be sharing. There's our covalent aspect. But are they sharing equally? No. Okay, so what ends up happening is we get what's known as a polar covalent bond. Okay? So there's now an unequal sharing of electrons. Okay? There's the potential for each of those people in the couple to interact with somebody else in the world. Okay? Ideally, that doesn't happen if we look at our relationships, but, you know, stuff happens. Okay? Same thing happens with chemicals. Okay? Those atoms are not equally sharing electrons, so they potentially interact with the rest of the world. That interaction with the rest of the world we refer to as a dipole-dipole force. Okay? What happens if they aren't married? They're just dating, seeing how things are. Okay? Well, theoretically, and I've never been there, but let's just say this was the case. You're dating someone, but you haven't made it exclusive, right? So what else are you doing? Dating other people. So you're interacting with a bunch of different people because there's not a strong attraction. Right? Or not a strong attraction yet. So what happens? What kind of bond does that become? That's now an ionic bond. An ionic bond because you aren't equally sharing each other's lives. Okay? That ionic interaction then says you can interact a lot with the rest of the world. That's going to generate that kind of force. Okay? Or our ionic or electrostatic force. Okay? So we have ionic bonds, polar covalent bonds, and nonpolar covalent bonds. When we look at an individual structure, okay, there's tons of atoms within it. This analysis is literally only looking at 2 atoms. So what you would have to do is pick 2 atoms and evaluate that relationship. Right? And then decide, is that an important relationship to evaluate? Or is it irrelevant to the overall molecule? Right? So it's always a 2-atom approach. Well, if I give you 2 atoms, how do you know it's a nonpolar covalent? How do you know it's an ionic? How do you know it's polar covalent? I can kind of accept that, so let's drop an example in here. If I give you the compound NaCl, take sodium atom and chloride atom, and I make them interact with each other, there's that bond representing it. Where on the periodic table does that tell me the bond between those 2? So the first thing that we could look at is, well, it doesn't say sodium chloride on the periodic table, right? So that becomes a questionable establishment. What are you suggesting? We've got classifications all the way back from Unit 1. Okay? Along that staircase, everything to the left of that staircase is a metal, and everything to the right of that staircase is a nonmetal. I have a metal in sodium and a nonmetal in chloride. Okay? The rule that we memorized when we did nomenclature back with Chapter 6 is that that is now an ionic bond. There it just popped up. Okay? So we have a metal and a nonmetal. That can help us figure this out. Why does that make it an ionic bond? Ionic means ionic means ion. What is an ion? A charged species. You look at sodium chloride, is it charged? Should I write positive or negative on it? No. Perfectly balanced. There's no charge. But we're calling that ionic. How do I know that's charged? What dictates that there's charge in there? We have this property known as electronegativity, the ability for an atom to take bonding electrons from another atom. Chlorine is very electronegative. Sodium is very not electronegative, which means the difference between those is massive, which suggests that the electrons in that bond spend most of their time with the chlorine, which means the chlorine just gained sodium's electrons, which means it becomes, you gain an extra electron, you would become negative. The sodium just lost its electron, which means positive. Now I see those charges. They become more apparent. So when you go through and look at compounds, thinking about splitting it and saying where do the electrons prefer to go is a really important thing to do, particularly if anybody has to move into OChem. That's the point of OChem, is saying where are those electrons going. Okay? So we have that ionic interaction. Okay? The rule of thumb that we could use, because we don't want to memorize electronegativities to look at that difference, is that if we take a metal and a non-metal, we have an ionic bond. Is that always true? No. 95% of the time, it's true, which means we can get away with just using it outright and just being happy with it. So if I look at a molecule that has a metal and a non-metal, I know it has an ionic bond, and I therefore also know that the force that molecule exerts on its environment. When I now take a look at one of the atoms of that molecule, and I look at another molecule and how those two molecules interact, is now electrostatic. Okay? That's what it means. Well, how about polar covalent and non-polar covalent? Because we want to be able to, again, find where do I get the dipole-dipole? Where do I get London dispersion? Right? Well, I know dipole-dipole comes from polar covalent. Well, how do I know it's polar covalent? I know London dispersion comes from non-polar covalent. I know that 80-year-old couple's not going to interact with the rest of the world, okay, because they've been married for 80 years. Right? And that would just be heartbreaking. Pretty much at that point, you've got to be like, we just got to sacrifice this out the rest of the time. Right? We don't want to split up now because, like, what are we going to do? Right? How do I know for chemistry that I've got a molecule that doesn't interact with the outside world? One thing, I could throw the molecule in with a bunch of other things and see what happens. What would I expect to happen? Nothing. I would get no reaction. Okay? So I could test it. That is a possibility. Okay? But the whole point of science is being able to predict what would happen and be right. Okay? To guess and be like, yep, I know I'm right. That's what you do on a test. You take an educated guess and you're like, I know I'm right. Not, I have no clue, I'm going to guess C. Okay? We want a solid, educated guess. Well, looking at the force is a test. Looking at the bond could help me out. Well, how do I know I have a non-polar covalent bond? They're equally sharing their electrons. Ionic bonds were not equally sharing. Why were they not equally sharing?
Because they weren't 100% connected to each other.
Why weren't they 100% connected to each other? Yeah.
Because there wasn't an attraction fully.
Yes.
Help me out, people.
Because difference in electronegativity.
Okay. One rule, we could use metal and non-metal. They were two different pieces of matter. That different interaction caused an unequal sharing. Okay. That's really kind of the hand-wavy 130 rule. If we take it a step further, we look at electronegativity, because electronegativity is a direct measure of that. Okay. That's why we classify metals as metals, is because they don't have high electronegativities. So I could look at the difference in electronegativity. For a nonpolar covalent bond, they are equally sharing electrons, which means what should the electronegativities be for both atoms? The same. So there is no one atom taking electrons from the other. Okay? Well, how would I know I have the same electronegativity?
Same element.
Okay? I could look to see, do I have the same element? Okay? So fluorine, the most electronegative element known to man and woman. If I bond that to hydrogen, That difference is now so astronomical that is technically an ionic bond. Okay? So I would predict if I put fluorine near anything, it's going to be an ionic or polar covalent bond. But what if I bond it to fluorine? Now what is that attraction? Non-polar covalent. It's the same element bonded to the same element. They're equally fighting for those electrons. That's a non-polar covalent bond. Okay? That definition is phenomenal. It works. It's great. However, it is insanely narrow. Okay? So if we go back to our difference in electronegativity, the rule, it depends on who you talk to, that for a non-polar covalent bond, the difference in electronegativity must be less than 0.5. What is the electronegativity of fluorine? I need to know that. No, you don't need to know that. So
What? We don't know.
you don't know. Okay. Do you want to memorize those? No. Okay, good. I agree. I don't want to memorize them either. Okay. So what we want is some other way to be able to identify it. Same element works, but how do I account for that 0.2, 0.3, 0.4 difference? Okay. Well, the rule of thumb that we go through and use is same element to same element and carbon bonded to hydrogen. Those are the only two cases that we classify as non-polar covalent. Is that true? No. There are plenty of situations where I can bond different elements to get a difference in electronegativity less than 0.5. However, I have to go searching and work for those. How many of you want to go searching and work? Okay, no, so let's not do that. There's our rule. So I know what an ionic bond is. I know what a non-polar covalent bond is. Well, what the heck is polar covalent? Everything else. Right? Anything that did not fit into the either metal and non-metal category or same element or carbon to hydrogen now becomes my definition for polar covalent. So this means I can now look at a structure of a compound, okay, or a molecule, quickly classify the type of bond, which then tells me the type of force. So if I look at, let's not do that because that's too complicated. I don't want to draw it all out. Methane. What type of force would I expect in methane? If I take methane and have it interact with something else, or try to see if it interacts with something else. How do we know London dispersion? Carbon and hydrogen, neither of them are metals, so it's not ionic. I can move to my nonpolar covalent category. Carbon to hydrogen is nonpolar covalent. I know the bond is nonpolar covalent, which means London dispersion force. Okay. That is the 80-year-old couple. Does it interact with anything? No. Nope. Doesn't interact. Okay. That interaction is so low that we initially looked at it and we said, it's never going to happen. We aren't going to worry about it. Okay. But it turns out that those couples that have been married for 80 years, 1 out of 1,000 of them actually does break up. Okay. And not because one of them died. They're just like, I'm done with you. 80 years, whatever. I got Fountain of Youth. Or I live forever. Or I'm Benjamin Button. Whatever you want to do. You're too old now. Okay. Come up with whatever you want to. That couple splits. So there is some case where it doesn't match perfectly. Okay. So I have to take that into consideration when I look at molecules that have nonpolar covalent bonds. It does happen. So I need to define that force. Because the world said, it's not going to happen, the person that comes through and says, actually, yeah, here it is. Here, it did happen. They get to name the force. That's why we get van der Waals, who was the discoverer. What Isaiah said? Okay. The one that quantified that force and said it was important. Okay. Why do we call it London dispersion? I really wish I knew the history on that. I don't. The dispersion makes sense. The London, I don't know. Because he liked bridges, right? London Bridge. Yeah. Okay. The dispersion really has to do with electron clouds, and if you move into 151, they can make it more complicated or a broader picture to explain what's happening with that. At this point, you just need to be able to identify it. Okay. So what did this mean for us? Okay, the London dispersion force was insanely weak. Right? Shouldn't interact with anything else. But what was the nonpolar covalent bond?
Very strong.
Insanely strong. Why? It's so strong, it doesn't interact with anything else. Right? So what we're looking at in our types of forces is we move from an insanely strong attraction counterclockwise up through our list. London dispersion forces is still a force. Nonpolar covalent is still a force. Okay? But what we did is we subcategorized and we said, well, actually, those forces are so strong, I want to call them bonds. Those forces are so weak, I'm going to call them forces because I'm not creative. Right? Within that bond category, I see 3 sublevels. Right? Within that force category, I see 3 sublevels. Right? So all we're trying to do is categorize it out. You might say, well, that seems like a lot of work. What colors are in the rainbow? Roy G. Biv. Wrong. What? All of the colors are in the rainbow. Okay? And yet, what do we memorize? Red, orange, yellow, green, blue, indigo, violet. That's not all the colors. Why did we memorize those? Those are the main colors. These are the main types of forces within each of those categories. Okay? We tried to simplify it so that we didn't have to go through and said it starts with red, then brick red, or brick red, then red, fire engine red. I don't know another red. Diamondback red.
Maroon.
Maroon.
Red.
Red. Okay. Cardinal red. I don't have to know all of those colors. I just have to do it as a bulk category. These are red. The next category is orange. The next category is yellow. Okay. What happens on those interfaces between red and orange? Well, I get some intermixing. What happens on the interface between nonpolar and polar? I get some mixing. Okay. What we're responsible for doing is the bulk classifications, because those bulk classifications get us a crap ton of information. I can look at a molecule that has nonpolar covalent bonds, and I can predict that molecule doesn't interact with its environment. Right? I can take a molecule that is ionic, and I can be like, that one, that's going to cause some damage. Right? Being able to make those quick analyses and be right is what science is about. We tested it, we proved it, you now have to remember the proofs. Okay? Because trust me, you don't want to test, is acid a bad thing to splash on your face? That's a bad idea. We don't want to do that. Okay? So what we've got are these bonds and forces, and we're concerned about what they do. That's what this chart is trying to go through and show. We have our covalent bond. Notice it doesn't say nonpolar. Why not? Because I am lazy. Right? The nonpolar becomes implied because there's 2 covalents, and one I define as polar covalent, which means the other one must be nonpolar covalent. Okay? There's my strongest attractive force, okay? Or interaction. Let's just call it an interaction. Okay? It progressively gets weaker until I hit ionic. Then what happens? Well, then I cross the boundary between bonds and forces, and I'm now a force that progressively gets weaker still. Okay? And what I'm concerned about is now, how do I use this information? Okay? Well, phase transitions. I can transition from a solid to a liquid to a gas, right? Well, what's breaking when I transition between solid, liquid, and gas? Bonds. Okay? So when I take water and I boil water, H2O, it becomes H plus and O minus 2. So if I stuck my face over just a pot of boiling water, right, not like superheated steam, just pot of boiling water, my face feels like, not even feels like, it starts to melt because I have now splashed acid in my face. What? You're like, I'm not sticking my head over a pot of boiling water again. You did it already. Did your face start to melt because you stuck it in a vat full of acid? No. Is it breaking bonds?
Yes.
If it breaks bonds, we generate H plus. H plus is an acid. Your face didn't melt. Are you breaking bonds? No. What happens when I add heat to water? It stays water. How do I know that? What happens when I cool down that gas? I get back to the liquid water. I don't break bonds. What? Then what happened when I transitioned? What did I break? The force between the individual molecules. Okay? So phase transitions, melting points, the temperature at which we transition from a solid to a liquid or a liquid to a gas, are dependent not on the bond, but on the force. So if I understand something about forces, I can predict between two species which one should have the higher melting point or boiling point based on their strength of interaction. Really? Yes, it's phenomenally cool. To me, because I could see your eyes roll.
We use the force to know what happens.
That's even cooler, yes. We use the force to predict what happens. Between these two compounds, which one would I expect to have the higher melting point or boiling point? So I need to evaluate the force. Right? To get the force, I need to know the bonds. What are the bonds in H2O? Right, well, it's a hydrogen to an oxygen. Is that ionic? No. Is it nonpolar covalent? No. What does that mean? It's polar covalent, which means the force is dipole-dipole. Again, because I'm lazy, I'm just going to write D-D.
What does dipole mean?
I'll get to that in a second. Sodium chloride. What kind of bond do I have in sodium chloride? Ionic, because metal and nonmetal. What kind of force would I get from an ionic bond? An ionic force. Which force is stronger, ionic or dipole-dipole? Remember, our strength goes around the circle. So which one's stronger? Ionic. So to get that ionic substance to melt, I have to put in more energy because it's a stronger attraction. Which means its melting point and boiling point is higher. Is that true? What phase is water? A liquid. What phase is salt? A solid. Why would that be the case? The melting point for salt is so much higher than it is for water that what phase is it? A solid, whereas the water is a liquid. Okay? We can use this to help us predict phases for those individual compounds, okay, or to explain the observations we have. That's pretty cool to me. Right? There was a question about what is dipole-dipole. Okay? Really what you're asking about there is what are those individual interactions and why did we come up with those names? Because what dipole-dipole is the force generated by a polar covalent bond. That's what you need to know. Why did we call it dipole-dipole? Well, I gave you a story behind London dispersion, right? Because we thought it shouldn't exist, so we named it after the dude that discovered it. Cool. Okay. For ionic, what did we call it? Well, ionic. Why? Because the force and the bonds came from each other. So for dipole-dipole, why don't I call it a polar covalent? Because that's stupid. It's confusing. Just like for ionic. If I say you have an ionic, what do you think I'm referencing? Force or bond? Well, I don't freaking know. You didn't specify whether it was bond or force. Right? So we would have to be extra specific in that terminology, which is why on that previous slide you didn't see just ionic, you saw electrostatic. Electrostatic is now trying to be used as the term for the force to help us differentiate the bond from the force. Ultimately, we're in a gray area there. We're transitioning between colors, between bonds and forces. That's why that line is blurred. It is difficult to distinguish the ionic bond from the ionic force. It's literally that, I'm just saying, there's a line. It's black on one side, it's white on the other. It's not, it's gray. Okay? So what happens with the dipole-dipole? Well, let's look at a polar covalent bond. Okay, so give me a polar covalent bond. Okay, that's two bonds, but I'm going to guess you wanted OH, just because I'm being a jerk. I apologize. No, I probably shouldn't apologize, because I'm not really sorry.
I like honesty.
I had to think about it a little bit. Am I actually sorry? No. Okay. I'm concerned about the force, so what do I need? Another bond. Okay, so I'll show that other bond. Okay, there's two possible options for this. Whoops. I could show that as HO or OH. And I'm now talking about that attraction. Which of those two attractions is more important to evaluate, the top one or the bottom one? Why the bottom one? Because you're right.
The top one is same element, same element. So
I don't quite accept same element to same element. How did we know this was a polar covalent bond? Yes, you got an answer that isn't going to help you out. Because it's everything else. It's not ionic or non-polar covalent. Ultimately, what was our line? How do we distinguish the different bond types? It was due to electronegativity, the difference in electronegativity. If it was a metal and a nonmetal, what happened? The nonmetal took all of the electrons. The other one didn't. What happens in a polar covalent bond? Well, one has a higher electronegativity than the other. So that oxygen is more electronegative than hydrogen, meaning what happens to the electrons in that bond? They go to the oxygen. So I could go through and show this as a negative. And what would happen to the hydrogen? Positive. Okay? But I've now drawn ions, which would suggest that's an ionic bond. It's not an ionic bond. So I need to change my notation to make sure that's not an ionic bond. Yes, the oxygen is taking the electrons, but it's not taking all of them. It's just taking some of them most of the time. So it's not formally negative. Only some of the time it's negative. Okay, so instead of writing negative and positive, I could say some of the time negative and positive. Okay, or because that's a lot of words, I could do sought. Right? Some of the time. It's sought negative. You guys are giving me weird faces. You don't like that, right? Okay. Well, believe it or not, no other chemist liked that either. I suggested it, and they all thought I was an idiot. So instead, they came up with a different notation. That different notation was this. You're like, that's not any better. I agree. I like sought a lot better. What is that symbol? Greek alphabet, anybody? It's supposed to be a delta. When do we use deltas? Capital delta is a triangle. This is a lowercase delta. A lowercase delta is a change. Really what we're saying is it is a changing negative. It is a changing positive. So the real quick on this, why is the top one bad? That's also a changing negative and positive. That top one is bad because that is positive to positive. Not valid. The bottom one is positive to negative. That's a valid interaction. That's a strong interaction. Okay? I know, I'm done. And I'm sure the other class is pissed off at me too. Okay? I have two charges. I have two poles, a north end and a south pole. Two poles. Two poles sounds stupid, so I'm going to bring in my Greek letters, and I'm going to call this dipole. That one molecule is a dipole because it has two poles. What's the other molecule? A dipole. Because I am stupid creative, that force between them is now a dipole-dipole.